Welcome back to chemistry. I hope everyone had a wonderful winter break and you're ready to start again. We're on Unit 6, Day 1, so we'll need a new packet. Go ahead and get that printed out or have notes that you can take digitally or by hand, or if you would like, you can pick up a copy of the packet from Oak Ridge High School in the library foyer. But please be ready to go before beginning. Another quick note, we will have a fall refresher video that is available if you are new to Oak Ridge or you just need a refresher of some of the concepts from the fall semester. You can watch that now or you can watch that at the end of this video because your homework does cover some things that are reviewed from the fall. So let's begin. We're going to start off with talking about reducing ratios. This is something you've been doing in math class for years, and all I mean by reducing the ratios is that if you can simplify, we want you to go ahead and simplify. So let's try that out. Okay, so here I see 4 and 10. I can divide these both by 2 and simplify. So I'm going to go ahead and do that. Simplify it out, and that will give me a 2 and a 5. 4 divided by 2 is 2. 10 divided by 2 is 5. So when I simplify that, it gives me the 2 and 5. Same thing I did with number 2. I've got 5 and 15, and I can reduce these. I can simplify them by dividing them both by 5. 5 divided by 5 is 1. And 15 divided by 5 is 3. All right, this next one, number 3, same thing. I want to look and find a way to simplify it as much as possible. So I find a common factor to simplify. These can both be divided by 2. Okay, so 6 divided by 2 is going to be 3, and 8 divided by 2 is 4. All right, keep going. Try it out. What is their factor that we can simplify these both by? That's going to be 3. So 9 divided by 3 is 3. 12 divided by 3 is 4. And the one thing that you want to keep in mind if you have more than 2 is that you need them all to be divisible by the same number. Okay, so I don't want to pick, for example, say I'm going to simplify the 6 by dividing it by 2 because I can't divide 3 by 2. So no matter how many you have in there, when we simplify, you need to make sure that they can all be divided by the same number. So in this case, I'm going to use the 3. Okay, so I'm going to go ahead and start with the 6. 6 divided by 3 is 2. 18 divided by 3 is 6. And 3 divided by 3 is 1. And then same thing for that last one. So you've been doing this a long time. Hopefully that's fairly straightforward. Okay, so what we just learned is actually something called an empirical formula. This is the most simple formula of a compound. So with ionic compounds that we talked about last semester, we always wanted to simplify. Ionic compounds need to be simplified if possible. So always, 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 if you see your metal plus your nonmetal in an ionic compound, get it down to its empirical formula. On the other hand, covalent compounds use molecular formulas. This gives you the number of atoms in each of the elements present, and it is unreduced. So molecular formulas, we want to count each and every single molecule. That's why when we had covalent compounds, if you could simplify it at the end, you were not supposed to. We wanted them all counted. So let's compare molecular versus empirical. This is a molecular formula. If we wanted to simplify this, we could, right? So we would divide them both by 2. 4 divided by 2 is 2. 10 divided by 2 is 5. Okay, so there's my empirical formula. Molecular and empirical formulas aren't necessarily going to be different, and that's what I showed you in this next example. I can't simplify H2O because there's an understood 1 to be right here, and I can't divide that without making a half, and you never want to get to a fraction because you can't have half of a molecule. So it's okay if your molecular and empirical formulas are not different. That is not a problem. If you can simplify, you need to. So if I was looking at the next one, here's my molecular, and if I wanted the empirical formula, I would need to divide these both by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. Okay, so that would give me NO2. Okay, next one. I'm going to be simplifying. So 10 and 22, their greatest common factor, you want to be thinking, okay, you can't divide it by 10, but you can divide them both by 2. So if you take that, I'm going to go ahead and divide them by 2. So I would get C5H12 divided by 2 is, or 22 rather, 22 divided by 2 is 11. Okay. Next one, same concepts. We're just going through and finding our greatest common factor, and we're going to reduce by that. Remember in chemistry, the reason you don't see anything after the oxygens in either of these is that there is an understood subscript of 1. Okay, so it's not that there are no oxygen, it's just that 3 divided by 3 gives you 1. And here, once again, it's okay if they match, right? You can't always reduce. So if you can't reduce it further without making a fraction, that's okay. The molecular and empirical formulas may be the same number, and that's okay. Okay, so here we go. Same thing. Here's my molecular formula, and I want to reduce it. Let's get that going. So my empirical formula would be C, let's see, what can we reduce these all by? That would be 6. 6 divided by 6 is 1. We don't write ones typically in chemistry, so I'm not going to put a subscript there. 12 divided by 6 would give me 2. And once again, 6 divided by 6 is going to give me 0. Okay, next one. We're going to divide them both by 2. So I would have C2H5. Okay, next, we divided these by 2. So 8 divided by 2 is 4, and 18 divided by 2 is 9. So we're just reducing when we can. All right, next one, it says, what is the empirical formula of x3y12? And so I'm going to take this 3, they can both be divided by 3, which would give me 1, and 12 divided by 3 would give me a 4. So I will pick choice D. Okay, a hydrocarbon has an empirical formula of CH3. The most probable molecular formula for this compound is what? So you want to, this is a good question because you have to kind of work backwards. This is already the reduced one. The empirical formula means it's already been reduced. And we just want to find the choice that's an answer that has, if we reduce them, it would match. So one method that you can do is to reduce and see. So I'm going to take this one. I've got a 4 and a 6, and if I reduce them, I'm going to have a 3. What? No, I'm not. And if I reduce them, I'm going to have a 2 and a 3. Okay, that does not match. So it can't be this one. I'm going to cross off choice A. Okay, let's reduce this. We've got a 2 and a 6. I can reduce these by dividing both by 2. That would give me a 1. And 6 divided by 2 is 3. Wow, look, it matches. So it's choice B, but we're going to go ahead and work through the rest so you can see why. See how when we reduce this, they match. So we worked backwards. This could be a molecular formula. Okay, but I'm going to work through the rest of the answer choices just so we can see. 3 and 8, I can't even reduce that, so this is not going to work. 3 and 8 do not have a common factor, so we're not going to use that choice. And we also can't reduce this one. It's already reduced, so it can't be choice D. So you just want to look through your choices and find, if your question is like this, reduce them all and find the one that matches. Okay? If you reduce it, it should match what the question wants. Okay. Now we're going to go do some scientific notation. Okay, so we're going to learn to express large and small numbers in scientific notation. Here is a penny. Look at all these atoms that it contains. That's a lot. Okay, that's a lot of zeros. Okay, this is also a lot of zeros, but going the other direction. The length of these numbers makes them very awkward to work with, and scientific notation can help us out. So instead of writing all these zeros, we can write it differently. Just to make it easier on ourselves, we can count and figure out the amount of zeros. It's much easier. So this number right here is actually the amount of the number of atoms in a penny. So it just takes all these and we can shorthand it to a number that's much more accessible. So that many places. And the size of each atom, same thing, just the other direction. Okay? So that is why you see this negative up here versus the positive number. This number is really, really large, while this one is really tiny. Okay? So a sign on the exponent tells which direction to move the decimal. A positive exponent means move the decimal to the right. Okay? So move the decimal to the right. So it's going to go out this way and be very large. If you see a negative, you're going to move it to the left, and you're going to have a very small number. So here's how we can do that. Here's a positive exponent. We're going to move it to the right and make a large number. We're going to take it and go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then that's going to be the ending. And then we'll do the exact opposite for a small number. Okay, you're going to take your number here and move 1, 2, 3, 4, 5, 6, 7. Drop it down and then you can fill in your zeros. See how we did that? Okay, so that will make a really small number. So if we're writing it in standard notation, this one, I'm going to look here, I'm going to move to the right. So 1, 2, 3, 4, 5, there. So if you see a positive exponent, you're going to move to the right. If you see a negative exponent, you're going to move it to the left. So drop down and then move 1, 2, 3 places. And then fill in your zeros. Okay? Negative exponents move to the left. And here's some more practice. We moved it here. You see it's positive, and you're going to move to the right. So even if it's negative in the front, that's okay. It's positive right here. So 1, 2, 3, 4. And that's how we came up with this number, negative 20,100. So you're not using this in the front. You want to make sure you're paying attention to the exponents, whether it's positive or negative, to figure out which direction to go. And then once again, a really big number, positive exponent, we're going to move to the right. Negative exponent, you're going to move to the left. So very small number. Anytime you see a negative exponent, your number is going to be less than 0, okay? So, more examples. This one, moving, if we're going the other direction, if you want to have both ways, right? If we say convert this to standard notation, or if you're saying convert it to scientific notation, you're just going to be moving and watching left and right. Okay? So, it says, our next one says, write 0.00709 in scientific notation. What you want to do is to make sure you only ever have one number in front of the decimal here. Okay, we only ever want one number in front of the decimal. So we need to drop this. 1, 2, 3, 7.09 times 10 to the negative 33. Okay, and then there it is. And here we go again. If you're translating this, and we need to make it, this is a very large number. I know it's going to move to the right because this number is much larger than 0. Okay, whereas this one was less than 0. So that's how I knew it was going to be a negative exponent. This one's very large. It's much bigger than 0. We only ever want one digit in the front. So I'm going to make sure I'm going to move all these places, 10 places, so there's only one digit in front of the decimal. Okay? So that ends up being 8.24 times 10 to the 9th. 8.24 times 10 to the 9th. So that's how we're going to do that. Here's some practice. It says write in standard notation. Okay, so it says 1.72 times 10 to the 4th, and I got this, and so I'm going to just show how we did that here. We got 1.72 so I'm going to take this, I'm going to move it right here because I only want one digit in the front, and I need to move it 4 places. 1, 2, 3, 4. So that's how I got that. And this one, it's negative, so I did the same thing, but the other direction. Moved it to the left. 1, 2, 3. And then if we want to move it this way, we need to make sure that there is only one digit in the front. So I'm going to move it 1, 2, 3 places. 5.3 times 10 to the negative 3. Because remember, this is less than 0. This number is much greater than 0. Okay, so I'm going to have a positive exponent here. So 1, 2, 3, 4, 5, 6, 7. 5.7 times 10 to the 7th power. Okay, so for next time, pages 1 through 3 are due to upload. A separate Fall Concepts Review video is available if you need a quick refresher, because the first couple of pages do ask you a lot about ionic and covalent naming. So we put together a separate video to help you. Next time you will also have a benchmark. Okay, this is going to be the quiz grade that you have for the only item in the gradebook for the first couple of weeks of the semester. So I very much suggest that you watch that Fall Concepts Refresher video. This is from Conroe ISD. There aren't going to be any retakes, as that is controlled by the district. So you will be taking that next time. One way that you can help yourself review is to make a little brain dump. And you can put whatever you want on here. I usually do mine on periodic tables. This is a short, simple, thorough way to review and help you just kind of put together everything that you've learned from previous lessons. Here's an example of one I made. I just put a lot of basic things, and I'll leave this up in case you want to make one of your own. I labeled, especially I would recommend labeling your valence electrons that are here in the red versus your oxidation numbers. Okay, your oxidation numbers, because they're a little bit different. I wrote down my little shapes, linear versus trigonal planar versus, that should say tetrahedral up there. They look like squares. I wrote some notes about ionic versus covalent. Ionic is metal plus a nonmetal. Covalent are nonmetal plus nonmetal. And I wrote about prefixes are used in those names, whereas transition metals and ionic compounds will need those Roman numerals, and I labeled those. Okay. Other things you might want to label are the names of the halogens, noble gases, alkali metals, and alkaline earth metals. Metals, be thinking those are the cations, whereas your nonmetals are those anions. Okay, these are your nonmetals, and everything else over here is your metals. So I will, you can pause that and make one of your own. I highly suggest that as another way to review for your benchmark. We'll see you next time. Have a good day.